So today, I want to share with you a particular case which my friend referred to when a shaft of his pump has failed. So what we did was that and he has sent the photographs also only. So initially what we did was that we input these photographs here in the AI, IndusDiagBot. So he required, this is what he said, send, need help of the bot to know major cause of failure of shaft. It is a pump handling corrosive acid. So to which I added the prompt, what is the failure mode, what is the cause, and then I extended the prompt, list the contradictions as in contradiction driven engineering. That is what this bot is supposed to think, the way in which this bot is supposed to think. Contradiction driven engineering, or CDE, of a pump shaft handling corrosive acid and the resolution of the problem. So we want the cause. The cause is always an unresolved contradiction that is existing. So we want to find that contradiction and then how to resolve this problem so that the frequency of failure or the number of failures reduces. So the bot comes up with diagnosis of the shaft failure in pump handling corrosive acid. Based on a photograph evidence and system documentation, here is a structured diagnosis. So what is meant by system documentation? The documentations or training schemes that has been by which this bot has been trained. Shaft fracture initiated by corrosive fatigue with possible torsional overload. So it lists three possible causes. First is the corrosive environment. Continuous exposure to corrosive acid weakens the shaft material, leading to stress corrosion, cracking, SCC, or corrosive fatigue. Dynamic loading or misalignment. Torsional vibration due to unbalanced or misaligned impeller can induce cyclic stress, accelerates fatigue crack growth. So torsional vibration is acting as an accelerator. So what is the initiator? Initiator is that it is working in a corrosive environment, so that initiates the problem. And then what accelerates the problem? The problem is accelerated by torsional vibration due to dynamic loading or misalignment. What is exactly the situation that we have not yet uncovered? And what is the inhibitor? That means what will increase the life material compatibility. The shaft material likely lacks corrosion resistance. So the shaft material has to have corrosion resistance. It seems that it is a standard carbon steel in acid, working in acid environment. So if the material is the right match, then it will reduce, or it will slow down the failure progression. So then it gives the supporting evidence. Failure surface shows typical beach marks, that is a fatigue. Beach marks are the sign of fatigue, and brittle fracture edge. Now these two signs, one is the beach mark and the other is the brittle fracture edge, consistent with fatigue under corrosive attack. So the edge has a brittle fracture, so that is consistent with the fatigue under corrosive attack. Pump applications plus corrosive fluid is high risk of stress corrosion cracking or acid pitting fatigue. If sudden, it doesn't still know that whether it was sudden. If sudden, check for torsional overload or start-stop shocks. So recommended inspections. Now it is recommending inspections. Shaft surface, visual, and SEM, scanning electron microscope if available, so that you can see the serrations and you can come to a better conclusions. Shaft material, metallurgical analysis, spectroscopy. Loading behavior, vibration, and torque analysis. So from the vibration analysis and the FFTs, we can understand the dynamic behavior. Acid chemistry, check pH and chloride levels. Then it starts recommending the maintenance and the design fixes. So the first fix that it is telling is retarder. That means something which will stop or prevent the failure, that is material upgrade. Switch to duplex stainless steel, Hest alloy, or acid-resistant alloys. Then it is providing a additional fix, additional prevention. That is coating. It is recommending a coating, apply acid-resistant polymer coating. Example, Teflon line shaft. Then it tries to deal with the dynamic thing, the torsional thing, the alignment check, precision alignment of pump motor coupling. Seal system, so that the acid vapors are stopped. Seal system improves sealing to minimize shaft exposure to acid vapor. Torsional damping, add coupling with damping properties. Okay, so these are the suggestions it is giving. Now what we prompted was that show us the contradictions that drove to this failure. So contradiction was stronger shaft versus corrosion resistance. A stronger alloy may lack corrosion resistance. Okay, so resolution is use duplex stainless steel, so it is strong enough and at the same time it has corrosion resistance, or coated high strength shaft. Coated means like the Teflon coating, acid resistant coating. Second contradiction, high strength versus manufacturability. If you have very high strength, it is difficult to machine it and manufacture it. So exotic alloys harder to machine. That is the manifestation. So use surface treated standard shaft, example nitrided or coated. So that can give you strength as well as manufacturability. Material stiffness versus vibration damping. So these two are related. So material itself should be able to resist the vibration and absorb it. So stiff materials transmit shock loads. So use damped. So how do I nullify it? Use damped flexible couplings to isolate the torque. Shaft tightness versus maintenance ease. Better seals reduce ingress but harder to replace. So use modular cartridge seals, that is the recommendation resolution, with accessible design. Redundancy versus cost. Backup systems reduce downtime but increase cost. So if I have a standby or redundant systems, I definitely improve the availability, but I also increase the cost. So the resolution is use condition monitoring, vibration and corrosion sensors instead of over design. So that is the resolution it is recommending. Now it is asking if you can share operating data, vibration, acoustic emission, torque trends, or chemical specs of the acid. I can simulate RUL, that is residual useful life, and confirm failure onset progression. Would you like a TRIZ-based redesign sketch or RUL model using signal data next? So I don't have the signal data, so I don't ask for it. But what I ask is, first give me a list of 10 questions to ask from the analyst, that is my friend, about this failure. Also note that the fracture has happened outside the enclosed area of the pump, not directly in contact with corrosive fluid. Is the analysis still correct under this condition? If so, how? So I am questioning its finding and recommendation. So it pats me on the back saying, excellent clarification, let us address both parts. Is the analysis still valid? Yes, but with important adjustments. Now, with inputs, it keeps on adjusting. The bot learns and then adjusts. Although the fracture occurred outside the wetted zone, several mechanisms can still apply. Indirect corrosion exposure. Acid vapor or mist can escape seals and migrate along the shaft to the atmospheric site. So for stress corrosion cracking to happen, it has to be in an environment where there is acid vapor. That's all. It need not be directly in contact with the acid. Second, it gives commonly in poor sealed or misaligned pumps where shafts, sleeve or seal faces wear prematurely. If there is a wear of the sleeves or the seals, then acid vapors will leak out and that can form the initiate the shaft fracture, brittle fracture. Stress corrosion cracking from atmosphere. If the shaft area is frequently cleaned with water or exposed to condensate plus acidic residue, stress corrosion can initiate from the outer surface flaws. So it is definitely an initiator. Micro cracks grow under cyclic torsional and bending loads even without full immersion. So full immersion is not a requirement. Torsional fatigue alone. Now it is eliminating the first possibility and concentrating only on torsional fatigue alone. What happens if only torsional fatigue was there? If chemical action is minor, failure may be mechanical fatigue driven by torsional stress concentration, often at, so it needs the stress concentration zones. So what are these keyways? Step transition, coupling junctions. So the combined effect of the acidic vapor and the torsional fatigue, there is a combined effect. Minor corrosion pits notch sensitivity, reduces fatigue limit, and crack initiates at the surface flaws. And mechanical torsional fatigue propagates the crack with fracture. But remember that I asked that give me 10 key diagnostic questions to ask the analyst or my friend. So it asks about seal condition. Was there any evidence of seal leakage or acid mist escaping from the pump casing near the shaft exit? It requires visual monitoring. Vibration history. Were there any high torsional or axial vibration events logged near the time of failure? So it is asking my friend to find out. Material specs. What is the exact metallurgy or hardness of the shaft? Was it tested post failure? So after the failure has happened, did the metallurgy change in any way? Did the phases change? Is the hardness drop? Previous surface condition. Was there any surface rusting, discoloration, or fretting observed near the fracture before the incident? Environmental exposure. Was the shaft any exposed to acidic vapor, washdowns, or open drainage systems from where the acid vapors can come? So it is connecting it to the environment. Environmental exposure. Possible environmental exposure routes. Fracture origin location. Was the fracture initiated from a known stress concentrator like a keyway, fillet radius, or thread root? Shaft design review. Were there any geometric discontinuity, steps, shoulders near the breakpoint? Load analysis. What were the transient or peak load conditions? Was there any peak load condition, transient load condition, any abnormal start-stop events, flow surges, or cavitation? Were these accelerators present in the situation? That is what it is asking. Protective coating. Was the external shaft portion coated, passivated, or otherwise protected from the environment? Historical failures. Has this pump or sister units experienced similar shaft failures or degradation patterns? So it is asking for a history. Based on your answers to this, I can refine. So the bot can refine or based on more inputs. So it is asking for visual clues. It is asking for vibration analysis. It is asking for test results. I can refine the root cause logic tree and provide precise resolution plan or run a fatigue model. It can do a fatigue modeling also. Would you like a template to fill out or proceed with the fault tree? No, I didn't do that. I just copied the questions and posted it to my friend to find out. So next prompt I give, refine the root cause logic tree and provide precise resolution plan and run a fatigue model. Would you like a template to fill this out? Record with fault tree, trees modeling. So I'm asking for trees modeling. Step 1. Pump shaft failure analyst input form. Shaft fracture location, example. So it is asking for details. So which the details are still not there. Let me know once it comes. But it has redefined the root cause logic tree. So the event is shaft fracture. So there are two possible routes. One is a corrosive fatigue. The other is a pure torsional fatigue. So if you go by the corrosion fatigue route, then acid vapor exposure, then acid migration post seal, then pitting of the surface flaw, that is going to create the surface flaw, the initiating points of the fracture, crack initiation and propagation. That is one route. The other route can be purely torsional fatigue, design stress rises like stress concentration zones like keyway fillet notch, high torque or startups. The pump is operating at high torque, or it is subjected to frequent stop starts, crack initiation, and fatigue failure. So this can be a root. The other possibility is that both together, combined way, it can accelerate the failure. Often both branches operate parallel. Slight corrosion accelerates fatigue in the stress zones. So one is helping the other to accelerate the fatigue crack. Precise resolution plan. So now it is giving a precise resolution plan. Material upgrade to duplex stainless steel or acid-resistant coated alloy. Shaft geometry. Eliminate sharp shoulders or keyway stress risers. Apply fillet radius, stress groove, stress relief grooves. Sealing systems. Replace with cartridge seals or double mechanical seals with atmospheric barrier fluid. So it is giving a suggestion. Protective coating. Use epoxy polymer shaft sleeves or plasma process nitriding, where a very thin layer of nitride can be deposited, and passivation, plus passivation. Vibration control, rebalance pump, align motor, and consider torsional damping couplings. The couplings which can damp the torque and torsion, and it will prevent the vibration from shaft from getting affected by the vibration. Environmental isolation, install shaft cover bellows to block ambient vapor exposure. Now, this is also a good suggestion. Condition monitoring, add AI plus IR, infrared thermography plus vibration sensors on the shaft exit to catch early degradation. So resolution trees based contradiction and resolution map. So this we have done again earlier. Use duplex, same thing. It comes up with use duplex stainless steel, surface coating, flexible or damp coupling. Use quick replace cartridge seals. Use breathable yet acid resistant bellows. Breathable yet acid resistant bellows. So fatigue model, it is saying that ready to run once inputs received. So once my friend sends me the inputs, it will do the fatigue modeling. So what it requires for doing the fatigue modeling, shaft geometry, material SN curve or estimate that it can estimate by itself, torque load variations that my friend can get from DCS, vibration RMS or AE spikes if any. So what it will simulate? It will simulate the fatigue crack growth, Paris law if applicable, estimate remaining useful life, RUL under cyclic loading, comparison of different material and geometry upgrades. So it can compare. Once you change the design, you can compare that how much extra life you will get. So in the meantime, my friend sends a Weibull analysis report he has done for this pump, which shows repeated failure. So my prompt is, this is a Weibull analysis of the pump shaft. Does this help refine the analysis already presented by you? It says yes. Now with some more input, Weibull analysis report significantly strengthens and refines our earlier fatigue diagnosis and planning. Here is how. So beta shape parameter is 2.05, indicates wear out failure mode, typical of fatigue, progressive corrosion, and cumulative misalignment effects. Eta, the scale parameter, is 147 days. A very characteristic life is 63.2% of the shafts will fail within 5 months, confirming a repetitive degradation mechanism. So the degradation mechanism is repetitive. Diagnostic implications and enhancements. Fatigue confirmed as dominant mechanism. Beta greater than 1 rules out random or infant mortality. Strongly supports our earlier mechanical fatigue hypothesis, likely accelerated by acid vapor exposure or torsional stress. Progressive damage preventable. This is not a sudden overload or one-off corrosion attacks. Failures accumulate from cyclic stress, alignment shifts, or vibratory torque over time. Recurring pattern validates design process flaws. So if it is happening, since it is happening again and again, so it validates that there is a problem with the design and the process. Since multiple shafts failed within months, the problem is systemic. That means the problem lies in the system, either in the material choice, sealing strategy, or misalignment practices. Failure modeling is now quantitatively grounded with with a characteristic life of 147 days and beta 2.05, we can fit this Weibull distribution into a probabilistic residual useful life model once load and geometry data are supplied. So it needs load and geometry data. So it now updates the resolution plan with maintenance strategy, vibration management, RDL estimation, seal and shaft housing audit, shaft redesign, material upgrade. So this is must. Next step is fatigue RDL calculation. So what I give a new prompt, update the fault tree and trees diagram with the probabilistic input. Now, since failures are never deterministic all the time, it is mostly probabilistic. So I am asking it with a new prompt. Absolutely with the Weibull parameter and this, so it improves upon the fault tree probabilistic thing. So material weakness, stress concentration from the torsional side, corrosive side, seal efficiency, acid vapor. So it gives us all the possibilities that have accelerated the fatigue. So mechanical fatigue path is dominant, but environmental acid attack acts as a secondary amplifier or accelerator, especially if the seals and coatings fail. So it gives an updated resolution, updated solutions. So the solutions are use flexible coupling, stress relief features, use bonded or diffusion coating that flex, use duplex material, stainless steel material, or nitrided high carbon steel, plasma coated, use double seals with vapor barriers and drain traps, decouple load bearing and corrosion exposed zones. So it summarizes. That means you see this, that it is giving you a monitoring solution. It is amplifier mechanism. It is identifying what is amplifying it. And then fatigue timing and shaft fatigue. So next prompt I give is first build a fault evolution simulation for shaft condition over time. So it is, I am asking for a simulation, fault evolution, how the fault is evolving over time. So it comes up with 3 graphs, the fault evolution simulation, pump shaft. So it plots the probability rate of progress of the fault against the days. So as the number of days goes up, the fault progression also rapidly accelerates. So now it gives a hazard rate over time, and it gives the reliability curve over time. That from these curves, from these charts and curves, we can find out a strategy that what should be my condition monitoring interval, what should be my PM interval, and what is the interval at which I have to change the shaft. Okay. So that explanation it gives, interpretation for maintenance and design. So it is recommending a replacement at 100 days so that we don't cross the line and suffer a sudden failure. Indicates fatigue is dominant, must control vibration and stress risers. So these two are the causes, important causes, but we still don't have the data. Shift from reactive to reliability-centered maintenance. Enables digital twin or computational intelligence-based RUL tracker. So it is suggesting that we can predict the decay by when if you set up a digital twin. So next prompt I give, or shall we stimulate what if design improvements? Now there are many design improvements it has suggested. So what if design improvements? Higher eta from alloy changes, yes. So that is the prompt I have given. So it has simulated that if you change the current design, that is giving us 147 days. Upgraded alloy, if you use, it will give 200 days. Alloy plus geometry, if you give, it will give 250 days. Alloy plus geometry plus coating, it will give us 300 days. So which is practically twice the MTBF that we are getting now. So that is a summary. Current design baseline, 147 days. So reliability at 150 days is 37%. Improved alloy, if I just improve the alloy, it will give me 200 days and the reliability is 61% will survive. Alloy plus geometry optimization, if I do both, then it will give me still further more days, 250 days, and 70% reliability at 150 days. Alloy plus geometry plus coating plus damping, if I do all of the four, which it suggested, it will give me 300 days with 83% survival probability. Each upgrade pushes the reliability curve. Full upgrade design more than doubles the expected survival beyond 150 days. This supports a shift from the reactive maintenance to condition-based maintenance with extended PM intervals. So instead of 180 days, I can do the PM intervals at 210 days. So next prompt I give is quantify the expected RUL gain numerically. So what is the expected RUL gain? And the next prompt I give, what insights we gain which are normally not available in standard textbooks and machine design textbooks. So it lists the new knowledge that we have gained, failure dynamics. Textbooks list fatigue modes, but don't tie them to actual failure probability evolution. Okay, so this is a new thing that it has done. Probabilistic design thinking. So textbooks focus on safe life or infinite life design, not field-driven probabilistic life. So textbooks don't give this. So that it has calculated. Hybrid degradation. Textbooks most design assume that only weighted parts corrode, that is the real world complexity. Trees contradiction mapping. Trees-based resolution isn't taught in standard curricula. It comes from innovative engineering, the resolution of contradictions. Weibull informed maintenance. Standard design tasks don't cover RCM intervals optimized via field failure analytics. Hazard curves are rarely taught, yet critical for knowing when to intervene. Digital twin readiness. Textbooks don't prepare you for data integrated computational intelligence powered diagnostics, which our AI can do very well. Economic layer. Traditional design does not embed lifecycle cost benefits modeling with reliability mass. So that is the additional thing that it has given. Okay. So it has summarized the case. So what the last prompt I gave, summarized lessons learned deck for RCA documentation. So ultimately it has to be documented. So it has given the full documentation of the case, which now can be stored, printed, used, and used for trading. Okay. So it gives us the root cause. It gives us beyond textbooks engineering insights. It gives us actionable corrective strategies and data-driven redesign. This is very important, data-driven redesign and PM decisions. And in that hidden thing, data-driven redesign, it has also revealed the contradictions that the shaft is suffering from, and it is giving us solutions to resolve those contradictions. Now it is asking me whether I read a PowerPoint format or a handout PDF or integrated into a reliability knowledge base or CMS system. So this is a new knowledge, so whether I'd like to include that into the bot's knowledge base. So that depends on me. So you see that this is the case study I just discussed. That was the intention of discussing the full case study, how to use an AI, how the AI is designed, and what is the background story of the AI on which AI gives us reasons and solutions and points out. Also the use of contradiction driven engineering, probabilistic redesigning, maintenance strategies and planning, and how do I improve the availability and reliability of the plant by taking these steps forward. So thank you so much. Wait for the next case that we should come up with.